Let's solve some heat transfer problems. In this first problem, let's look at heat transfer via conduction. Here we have the wall of a house. Because the inside temperature of the house is warmer than the air outside the house, we're going to have heat transferring through the wall. So we have a 6-inch insulated frame wall in a house that has an average thermal conductivity of 0.04 BTUs per hour foot R. That's degrees Rankine. The inner surface of the wall is at 68 degrees Fahrenheit, and the outer surface is at 40 degrees Fahrenheit. The temperature varies linearly through the wall. Determine this at steady state, the rate of heat transfer through the wall in BTUs per hour. If the wall is 20 feet times 10 feet, determine the total amount of energy transfer in 10 hours in BTUs. So here's what we are given. We know the thermal conductivity of the wall is 0.04 BTUs per hour foot degree R. The inside temperature of the house is 68 degrees Fahrenheit. The outside temperature is 40 degrees Fahrenheit. The height of the wall is 10 feet and the width of the wall is 20 feet. The length of the thickness of the wall, which is the direction that the heat transfer takes place, is 6 inches. And the area of the wall is the width times the height, or 20 feet times 10 feet, and that's equal to 200 square feet. We need to solve for the rate of energy transfer, which will be given Q dot, which is the rate of heat transfer, is Ka over L times delta T, where K is the thermal conductivity, the area is the area of the wall, L is the length or thickness of the wall, L is the direction that the heat transfers through the wall, and then we have the inside temperature minus the outside temperature. Okay, so Q dot is, substituting value, K is 0.04, the area is 200 square feet, the length or thickness of the wall is 6 inches, but let's convert that to feet. And then we have the temperature difference, 68 degrees Fahrenheit minus 40 degrees Fahrenheit. Now it may seem that there's a discrepancy here. This temperature difference is given in Fahrenheit degrees, and our thermal conductivity has R degrees in its denominator. Okay, well, there's something interesting going on whenever you subtract temperatures. When you take a temperature difference, you do not end up with a temperature. You end up with a number of degrees. So I've got a temperature of 68 degrees Fahrenheit, and I'm going to subtract from that another temperature of 40 degrees Fahrenheit, and that gives me what? 28 degrees Fahrenheit. Now 28 degrees Fahrenheit is not a temperature. It's a number of Fahrenheit degrees. So I can note that 1 Fahrenheit degree is the same size as 1 Rankine degree. Now that's not to say 1 degree Fahrenheit is equal to 1 degree Rankine. That is not true at all. But a 1 Fahrenheit degree has the same amount of temperature difference as 1 Rankine degree. So in that sense, then I can use, as long as this is delta T and not a temperature, this Fahrenheit degrees will cancel with these R degrees. So multiplying this out, we get that the rate of energy transfer is 448 BTUs per hour. Now let's solve for the total heat transfer in 10 hours. We know that Q is Q dot times time, because Q dot is energy per unit time. And we know that Q dot was 448 BTUs per hour, and we were given a time period of 10 hours. So in 10 hours, this house will lose 4,480 BTUs through that particular wall.